Welcome to the ET335 how-to video to do the practice midterm for fall 2025. Okay, let's do the first problem. It is a NOR gate. And let's go ahead and use our unique condition of 0, 0, which is going to be a 1. So let's find all our 0, 0s. There's 1. And wherever there's a 0, we're going to make it a high. And where there's not, there's going to be a low. Okay, let's compare it to the answer. There's 5 high pulses. Okay, here's our pretty answer, and we've got 1, 2, 3, 4, 5 highs. It looks correct. Okay, here we have a combination circuit of a NAND feeding into a NOR. So we're going to figure out the output of the NAND and then combine it into the NOR. So our unique condition is 1, 1. And we're going to get a 0 out. So wherever we have a 1, 1, we are going to get a low. So let's draw our lows. And everything else is a high. Okay, so now we have our NOR, and 0, 0 to 1. So we're going to look at our zeros. That is not a 0. 0, 0, not a 0. Okay, so we only have 2 peaks. Okay, so we have 2 pulses. Let's check our answer. Okay, here we have our 2 peaks, so it looks correct. Okay, here's our discrete decoder, and we are having our LED light with this single combination of entries. And since this one is providing a ground, it is a sync. Providing a ground. So let's go ahead and just use a NAND gate. And a NAND gate is going to require 1, 1 in order for us to get a 0. So let's go ahead and just use NAND gates. All right, NANDs and NORs. So that's a 0. And there's multiple ways for us to do this. So a 0 would be what? A NOR gate. And we could use ANDs and ORs. Okay, this is a 1. And this is 0, 0. So what do we have? A 0 and we want a 1. So let's go ahead and use another NOR gate. And like I say, there's several different ways to do this, but this was one of the ways that'll work. Okay, this is a different layout, but essentially it's got 2 1s into a NAND, 2 0s into a NOR. We take our 0 out of our NAND, put it into a NOR. We have two NORs, 0, 0 equals 1. 1 into that provides a low, which lights our. Okay, we're going to need our calculator for this. And we have a frequency of 1,000 hertz. So we need to find our period. Tau, period, equals 1 over 1,000. So let's turn it on. 1,000 inverse 1 millisecond, or 1,000 microseconds, since we're in microseconds here. So our duty cycle is our time high over our period. So we have 120 over 1,000, which is 12%. So our duty cycle is 12%. And our formula for our resistors R equals 10 times the pulse width over the capacitor. So R equals, our pulse width is 120 microseconds times 10 divided by 1 microfarad, and we work out the calculation, and it should come out to 1.2 megohms. Okay, there's our answer, 12%, 1.2 megohm, and it's an integrator based on this circuit. If we swap the two, then it becomes a differentiator. Okay, here's our standard totem pole circuit, and we want to sourcing condition. So sourcing was going to be V. So let's put a V here. If we have voltage here, that means L1 is going to light. In order to get voltage, we need to have this guy, Q1, on. And Q, actually it should be a 2 there, Q2 off. Okay, there's our answer, Q1 on, Q2 off, L1 on, lit. Okay, let's draw the circuit for this Boolean equation. So I'm going to do my best. So A plus B is going to be a OR gate. And C plus D is going to be an OR gate. Oops, C plus D. Somewhere or another we lost our parentheses. And since this is multiplication, it is going into a NAND gate. The NAND gate being the bar, the bubble eating the bar. So we have plus E, which is going to be a OR. With the bar, it's going to be a NOR. Good. And here we have our pretty CAD drawing. ORs addition, multiplication, ands and ands, and addition NOR. Okay, this Carnot map, and we need to go ahead and map in ones, so we need to convert our values here to make them all equal to 1. In this case, these are all going to be zeros. For a bar 0, 1, 0, 0, 0. This is going to be 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1. Let's go ahead and map them in here. Here's our first one. 0, 0, 1, 0 would be here. Next one would be 1, 0. 0, 0 would be there. Then we have 1, 0, 0, 1, which would be here. And 0, 0, 1, 1, 0, 0, 0, 1. And 0, 1. Oops, 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 oops. This is totally backwards, sorry. So this is going to be 1, 0, 1, 0. I don't know how I got that backwards, but I did. And which would be down here. Okay, so this would be a quad. And these two will be a quad. So let's go ahead and take a look at the first one. So we're going to have two values. So let's see what drops out. Look like which one stays? Which one does not change? It looks like bar. Let's see what it is. C and C bar. Bar. Stay. And what do we got here? So looks like nope, A's gone. We got a B bar. And what else stays? D bar, D bar. And let's double check that. Okay, here's our color-coded Carnot map, and we come with BC plus a B bar, C bar plus B bar, D bar was what we just got. Okay, let's go ahead and do the waveform of this JK latch. It has a preset and clear, which are asynchronous inputs, which will control the gate, disregarding the clock. And then we have JK pulled high, so it's a toggle mode. So first thing let's do is let's identify our preset. Preset goes high. Clear goes low, and negative edge, so we're going to toggle on our negative edges. Alright, so we're going to go here, toggle, we're going to jump right back up, and we're going to go until we get to the clock, toggle, toggle, and we're going to go till we get here, and then we're going to get our clear. Our clear is going to stay until we toggle. And we're going to toggle and out. So let's see how well we did. Okay, so we have our preset and our clear, and we toggle on each of the negative edges, and it looks correct while we okay, we're going to build a debounce switch by adding some components to this SR latch built from NOR gates. So with a NOR gate, we are going to use a low on our input. So we're going to put a ground here. And in order to keep these things from flipping in between, we're going to put pull-up resistors high. Pull-up resistors will go to voltage. And that'll keep it from flipping. So whenever we flip this switch, we are going to get a debounced output. And our beautiful answer matches.